We're looking at scaling text-to-image diffusion transformers with representation autoencoders by Shengbang Tong, Seining Ji, Yan LeCun, and their team.
Yeah, and this paper is a massive wake-up call for the generative AI space. It really fundamentally challenges the dominance of variational autoencoders, or VAEs, in latent diffusion.
So the headline claim is that representation autoencoders, RAEs, which use these massive, frozen, high-dimensional semantic spaces, they're just a better foundation for text-to-image.
A far superior foundation. And the results, I mean, they're undeniable. They report a 4.00x speedup on Genival and, what was it, a 4.6x speedup on DPG bench during pre-training?
Right, compared to something like FLUX. But for the engineers listening, I think the real killer feature has to be the stability.
Yeah.
During fine-tuning, VAEs just suffer from this catastrophic overfitting after maybe 64 epochs.
They just start memorizing everything. Whereas RAEs, they remain stable and performant through 256 epochs, all because of the implicit regularization of that huge high-dimensional space.
And then there's the final piece, this latent test time scaling. Because the RAE uses the same encoder for understanding and generation, an LLM can actually verify the quality of a generated image directly in the latent space.
Without ever decoding to pixels, it's a unified architecture. It makes the model faster, smarter, and honestly, significantly harder to break.
All right, let's get into the weeds on this.
Yeah.
This paper is proposing a really fundamental architectural shift. For the last few years, if you were building an image generator, Stable Diffusion, FLUX, SDXL, you had this one component you just assumed was necessary.
The VAE.
The VAE.
Right. It's like the engine block. You don't really question it. You assume you need a variational autoencoder to compress your data before you do any diffusion.
And this paper, with LeCun's name on it, no less, is basically saying, rip that engine out, it's the wrong part for the job.
Exactly. And to understand why that's such a big deal, we have to look at why we use VAEs in the first place. It's purely an efficiency play. If you take a raw image, say a 1024 by 924 pixels, that's a massive grid of data. And if you try to run a diffusion process directly on those pixels, calculating the attention maps, the noise removal, the compute costs are just astronomical.
It's just way too many tokens.
It is. So the industry standard became use a VAE. You compress that huge image down into a tiny latent space. Usually we're talking about 4 channels, maybe up to 64 in some of the newer models.
You squash the data.
Yeah.
Run your diffusion on the small data, and then inflate it back up.
It's like zipping a file before you email it.
But there's a catch.
Right.
There's always a catch.
The catch is what you're optimizing for. A VAE is optimized for reconstruction. Its entire goal in life is to make sure that when you unzip that file, the pixels look like the original pixels. It does not care what the pixels mean.
So the VAE doesn't know this is a dog. It just knows here's a cluster of brown pixels next to a cluster of green pixels.
Precisely. It's a compression algorithm, not a semantic understanding algorithm. And because you're compressing it so heavily down to just 4 channels, you inevitably lose high-frequency details.
Which is why they always struggle with text or fine textures.
Right, unless you do a lot of post-processing. And that's where the RAE, the Representation Autoencoder, comes in. The philosophy is completely different.
So instead of learning a compressor from scratch,
they say, let's take a model that already understands the world. In this case, they grab a pre-trained frozen vision encoder, specifically SigLIP 2.
And SigLIP is a contrastive language image pre-training model. It's trained to match images to text descriptions. So it already, knows what things are.
Exactly. It has seen billions of images. It knows what a dog is and knows what a sunset is. So when you feed an image into SigLIP, it doesn't give you a compressed pixel map. It gives you a high-dimensional feature map.
And when you say high-dimensional, you mean high.
We are talking 16 by 16 tokens, but each one of those tokens has 11,152 channels.
Wow.
Compare that to the 4 channels in a standard Stable Diffusion VAE. It's just orders of magnitude more data.
Now, historically, this is where people stopped. The conventional wisdom was that you couldn't do diffusion in a space that large.
They called it intractable. The idea was that the dimensionality was just too high, the space was too abstract, and the diffusion model, the DTATE, it would just get lost trying to find the signal in all that noise.
People thought the math just wouldn't converge.
Right. But this paper proves that not only can you model it, but it actually works better. And the reason is actually pretty intuitive. Because the space is semantic, the model has an easier time learning the relationships between concepts.
It's easier to learn how to draw a dog if you have a mathematical representation of dogness, rather than just memorizing pixel patterns.
You got it.
So we have this powerful encoder, SigLIP2, creating these rich, massive feature maps. But SigLIP's a one-way street. It turns images into math. It doesn't turn math back into images.
And that's the first big engineering hurdle they had to solve. They needed a decoder, a model that takes those 11,152 channel tokens and turns them back into a nice JPEG.
And usually in deep learning, if you need to train something new, you just throw a massive data set at it and wait.
That was their first attempt. They moved beyond ImageNet, which is clean but, limited, and they trained the decoder on web-scale data, about 39 million images. Plus, they generated a bunch of synthetic data using FLUX just to boost the volume.
39 million images. I mean, that sounds like plenty.
You would think. And for general images, landscapes, portraits, it worked great. The fidelity was high. But then they tried to reconstruct text.
Text. The nemesis of all image generator.
It was a disaster. Even with 39 million web images, the decoder completely failed at text reconstruction. If you fed it an image of a street sign, it would give you back like a geometric shape with alien gibberish on it.
But wait, if they scraped the web, surely there were millions of images with text in that training set.
There were, but the model wasn't incentivized to learn the structure of characters. It just treated text like it was texture like leaves on a tree or something. And it turns out, for the decoder, the composition of the data matters way more than just raw scale.
So how did they fix it?
They had to inject targeted supervision. They added a specific data set called rendered text, just pure typography and glyphs.
So domain-specific training.
Exactly. And once they added that, the decoder learned to spell. It's a crucial lesson for anyone listening who works on data sets. You can't just rely on web-scale scraping to solve these specific structural problems. You need domain-matched coverage.
That makes total sense. It's like trying to learn to read by skimming through a library without ever actually learning the alphabet. Now, there's another detail about the encoder I want to touch on. They didn't just stick to SigLIP2.
This was a fascinating ablation study. They wanted to prove that the RAE framework isn't just riding on the coattails of SigLIP's text alignment. So they swapped it out for WebSL Dino.
And Dino is a self-supervised model. It's purely visual. It has no text encoder, right?
Correct. Zero language understanding. And yet, when they plugged it into the RAE framework, it still outperformed the SDXL VAE.
So it's not about the text alignment. It's about the latent space itself.
It proves the robustness comes from the high-dimensional, representation-rich nature of the tokens, regardless of whether they are text-aligned or not.
Okay, so they have the encoder, and they have a decoder that can actually read and write. Now comes the hard part, training the diffusion transformer, the D-T, that actually generates the content.
And this is where they ran into this whole scaleless simplifier phenomenon.
I love this concept, because usually, as models get bigger, we have to add more hacks and band-aids just to keep them stable.
In the original RAE paper, which was done on ImageNet, a much smaller scale, they had to use all sorts of tricks. They had something called noise-augmented decoding and these wide diffusion heads, or DITDH.
Basically, extra parameters to handle the complexity.
Right. But here, they asked the question, do we still need these crutches when we scale up to 2.4 billion or, 10 billion parameters?
And the answer?
No. They threw them in the discard pile. They found that the wide head, where you add extra width to the output layer, it just became redundant. When your backbone is that massive, it's already wide enough to handle the dimensionality.
That is great news for engineers. Less code, less complexity.
Exactly. The benefits of those tricks just saturated and vanished at scale. However, there was one mathematical adjustment they absolutely could not discard. In fact, if you skip this, the model just breaks.
The dimension-dependent noise schedule.
This is the most technical part of the paper, but we really need to cover it. In diffusion models, you add noise to an image, and you teach the model to remove it. And the schedule of how much noise you add at each step is critical.
And the standard schedules were all built for VAEs, these small, low-dimensional spaces.
Exactly. Imagine trying to find a whisper in a small room. That's a VAE. Now imagine trying to find that same whisper in a massive stadium filled with people. That's the RAE latent space. The signal-to-noise ratio, the SNR, is completely different because of the high dimensionality. The signal gets drowned out much faster in the big space.
I see.
And if they use the standard VAE noise schedule, the Generative score dropped from 49.6 down to 23.6. I mean, the model basically collapsed.
So what's the fix?
You have to shift the log SNR. They derived a formula that shifts the noise schedule based on the effective dimension n times d. By shifting the schedule, you make sure the model is actually learning at every step, rather than just guessing through the static.
So for anyone implementing this, you can ditch the wide heads, you can ditch the noise augmentation, but do not mess up the noise schedule shift.
Write that formula down. It is absolutely non-negotiable.
So we have a simplified architecture with the correct math. Now we get to the showdown. They put this RAE up against the current heavyweight champion, FLUX.
And this was a rigorous comparison. It was apples to apples. They used the same text encoder QN 2.5, same DIT backbone architecture, same training data mixture. The only variable was the autoencoder.
And the results were pretty stark, especially on speed.
4 times faster convergence.
Let's just pause on that. In the world of training foundation models, 4x faster translates to millions of dollars in compute savings.
Or it means you can train a model that's 4 times better for the same budget. It's a massive efficiency unlock. And this scaling law held true whether they were training a small 0.5 billion parameter model or a massive 9.8 billion parameter monster.
But there was another scaling finding I thought was really interesting, and it had to do with the LLM, the text encoder.
Yes. They found that RAEs benefit more from scaling the text encoder than VAEs do.
So if you upgrade from, say, a 1.5 billion parameter LLM to a 7 billion parameter one, the RAE gets a bigger boost.
Exactly. The hypothesis there is that the VAE is a bottleneck. It compresses the visual data so much that even if the LLM provides a super nuanced, rich description of the scene, the VAE's latent space just doesn't have the bandwidth to represent those subtleties.
It's like hiring a Shakespearean actor to read a script, but you're recording them on a scratchy, low bitrate microphone. All the nuance is just lost.
That's a great analogy. The RAE, with its high-dimensional space, it acts like a high-fidelity microphone. It can actually capture and utilize the rich semantic information coming from the larger LLM.
Now, speed and scaling are great for pre-training. But let's talk about the practitioners, the people who are fine-tuning these models on custom data sets. This is where I think the RAE really shines.
This was the most shocking result for me personally. I mean, we all know the pain of fine-tuning diffusion models. You have to be so careful. If you train for too many epochs, the model collapses.
The images start looking like those deep-fried memes, oversaturated, high contrast, just weird artifacts everywhere.
That's overfitting. The model stops learning the concept and starts memorizing the noise patterns of the specific training images. They tested this on the BLIP 60K dataset. With the VAE models, they saw catastrophic overfitting after just 64 epochs.
64 epochs is nothing.
The loss curve just drops near zero, which, looks good on paper, but practically the model is ruined. It's just spitting back training data.
And the RAE?
They push it to 256 epochs. No collapse. They push it to 512 epochs in the appendix. Still stable.
That is absurdly robust. Why? What makes the RAE so hard to break?
It goes back to the difference between pixels and concepts. In a VAE, the latents are just compressed data very close to the pixel level. It's easy to memorize noise there. In an RAE, the tokens represent semantic meaning.
Dog, cat, red, blue.
Right. And it is much, much harder to overfit to abstract concepts than it is to overfit to pixel noise. The high dimensionality acts as an implicit regularizer.
So the fact that the space is abstract and intractable, the very thing that scared people away, is actually what protects the model during fine-tuning.
Exactly. It prevents the model from cheating.
This leads us to the final section of the paper, which feels a bit more like science fiction becoming reality, this one brain concept.
This is where we move away from the two-tower paradigm. Currently, we have an understanding model that sees, like SigLIP, and a generation model that draws the VAE. And they're separate. They speak different languages.
But in the RAE architecture, the generation model is built directly on top of the frozen understanding model.
They share the same brain. They speak the exact same high-dimensional language. And this raises a question. Does adding the ability to imagine hurt the ability to see?
Does the model get dumber at understanding images because it learned to generate them?
And the answer is no. They ran it on MMMU and text VQA benchmarks. The understanding capabilities remained completely intact, but the real magic is what this unification allows you to do. It's called latent test time scaling.
Okay, walk us through this, because this feels like a glimpse into the future of agentic AI.
So imagine you give the model a prompt, a futuristic city with flying cars. The DIT generates a few potential options in the latent space. Now, normally these are just meaningless numbers until you decode them.
And decoding is slow.
Very slow. But with an RAE, those numbers are semantic features. So you can take an LLM, point it at those latent numbers, and just ask it, how confident are you that these numbers represent a futuristic city?
Wait, so the LLM is judging the imagination of the model before it even renders the image?
Exactly. It's verifying the thought process, not the final pixel output.
That is wild.
They used a best-of-n strategy. The model generates, say, 10 latent representations. The LLM scores them based on prompt confidence or answer logics. It picks the best one, and only then do you run the decoder to get the pixels.
So you skip the expensive decoding step for all the bad ideas.
You decouple reasoning from rendering. They showed they could significantly improve GenEval scores without rendering a single pixel during that verification loop.
It's like thinking before you speak. You run through a few options in your head, you pick the best one, and you only say that one.
And because you're doing it in latent space, it's computationally efficient. It suggests that future models will have these kinds of verification loops built in as a standard feature.
So let's wrap this up. We are looking at a system that is 4 times faster to train. It's incredibly stable during fine-tuning, and it allows for this latent space verification because understanding and generation are finally speaking the same language.
It's a really compelling package. The VAE has served us well, but I think its days are numbered. The simplicity and the power of RAEs, especially at scale, are just too good to ignore.
It really makes you wonder where the line is drawn. If the model uses the same tokens to see the world and to imagine the world, are we reaching the point where computer vision and generative AI are just the same field?
I think we are. We're moving toward these unified foundation models where visual data is just another modality, another set of tokens handled natively by the core intelligence. No more separate towers, just one brain.
A fascinating future. We strongly encourage you to read the paper, especially if you're an engineer. The math on the noise scheduling is dense, but absolutely critical if you plan on implementing this.
Do not skip the ablation studies.
Thanks for listening to this episode of AI Paper Podcasts. We'll catch you on the next one.